Previously, we looked at how to find the area under a curve. For example, if you had this particular curve and you want to know the area between it and the x-axis, if this curve was continuously defined by function f of x, intersecting the curve at A and again at B, and you wanted to find this area, we have learned that you can just integrate from A to B. We can integrate f of x with respect to x, and from that we will get the area that we're looking for. All right, but the area that you're looking for will not always be conveniently defined as being an area between a curve and the x-axis. That will not always be the case. For example, what if we had two curves and we wanted to find the area that was between them, again, from a point A to perhaps a point B. All right, so therefore, just for visual purposes, the area that we would be looking for is area between two vertical reference points, two vertical lines, and between two curves. And for convenience, we will say that they are continuously defined, continuous curves on the interval from A to B. Call this one f of x, and call this one g of x. Now, if you were to look separately at the integral from A to B of f of x dx, what you would get from that is this area here that is above the x-axis. Now, since that area is above the x-axis, the result of this would be a positive value. Area, remember, above the x-axis results in a positive outcome. If we were to integrate from A to B the g of x dx, what you would get is this area down here. But again, notice that since that area is below the x-axis, the result of this integral would be a negative value. But the area we actually want is all of it, though. All of it. And from a very simple algebra, actually not even algebraic, but just simple numerical computation, we know that when you subtract a negative, you get a positive. So what we find is that if we simply subtract those two, just a simple arithmetic fact says that minus this negative will turn it into plus a positive. And then we can combine this into a single integral. And that is how we will define areas such as these. And you may think, or I wouldn't want to lead you to think, that this will only work when you have part of the region above the x-axis and part below. Because if you were to rethink the scenario, again, if this was curve f of x, and this was curve g of x, from A to B again, and again, here's our vertical reference here, our vertical reference there. If this is the area you want, right, then what would happen if you were to integrate f of x with respect to x from A to B, the area you would get would be this entire area. If you want to sort of draw a sample Riemann rectangle or two, the area you would get from that would be that area, which is actually larger than the desired area. It is including a region down here we don't want. If you were to integrate from A to B, the g of x dx, the area that would give you would be down here, which is actually not more than the region we want. It's actually the exact region that we didn't want. But what subtracting this g of x would do would be to remove from your calculation this region that we did not want. So once again, subtraction will accomplish that. And once again, the area between those two curves and also between those two vertical reference frames, the A and the B, is still going to be the integral from A to B of f of x minus g of x dx. Basically meaning that if you want to find the area between two functions that are both functions of x, I'm going to be clear on that. If it's the other way around, we're going to adapt and overcome to that. But again, in this scenario, it's going to be upper curve minus lower curve, and that will give you the area between those two curves. Now, for that reason, since it's always an upper minus lower type scenario, I think it is a good idea, whenever possible, to draw the curves and draw the region that you're trying to find the area of. Because if you are accidentally not taking upper minus lower, then things are not going to work out correctly. A prime example of when you have to be the most cautious is in a situation, let's say we want to find the area between the curves of y equal sine of x and y equal cosine of x from, we want that region from 0 to pi over 2. All right, so if that's what we wanted, again, as I've said, you definitely want to know what your region looks like. And of course, you know what sine and cosine look like. But just for a little bit of help from the calculator, if I put in sine of x, and then I put in cosine of x, and do a zoom trig with those, it will draw sine of x first. So we need to remember which one's which. There's sine of x. And here comes cosine of x. All right. And the area that they want, again, is from 0 to pi over 2. Well, pi over 2, I want to remind yourself, pi over 2 is roughly 1.5, 1.5, 1.57 technically. So if we go back and we start looking for 1.57, just to get an idea how far we're going, it's about right there. Well, it's exactly right there. So what we should be seeing is that for a little while, cosine is on top, and then they intersect, and from there on, sine is on top. So what you need to gather from this is that the function that's on top doesn't always stay on top. Sometimes they switch places. Now, technically speaking, there are a couple of ways to handle this. All right, we could say we're going to integrate from 0 to pi over 2. And what we saw on this graph was that cosine started on top. So we could say cosine of x minus sine of x dx. And to take care of the problem that occurs when they switch places, we could simply take an absolute value. All right, because when they switch places, what's going to happen is you're going to go from a larger number minus a smaller number to a smaller number minus a larger, which means you're going to go from positive to negative. You're going to start losing area where you should have been gaining. But the absolute value would fix that. The absolute value would fix the problem that, you're getting negative results. But putting an absolute value in there creates an entire another problem, because they will, as a matter of fact, they will define area as the integral from a to b of f of x minus g of x dx with the absolute value. All right, that is actually the ultimate and final definition of area between two curves. But again, throwing this absolute value on here takes us from something that we can easily integrate to something that's not at all easy to integrate. That creates a considerable problem. But if we were to remember that cosine of x is equal to sine of x at pi over 2. Oh, sorry, pi over 4. Pi over 2 is where we're going. Pi over 4, you get square root of 2 over 2 for both sine and cosine. All right, so they equal each other at that point. So that is the point over here, pi over 4. That 0.7 approximately is where they're hitting each other. All right, therefore that's where they're crossing. So instead of being forced to integrate with an absolute value in the picture, which creates an extremely complicated scenario, what we can do instead is we can integrate from 0 to pi over 4. And from 0 to pi over 4, it's the cosine that is the upper function, the function above, the one with the larger value. So we would simply integrate cosine of x minus sine of x dx from 0 to pi over 4. And then from pi over 4 to pi over 2, we could integrate sine of x minus cosine of x dx. And those integrals are ones that you should, by this point in time, be capable of doing. So I'm not going to evaluate them for you, but that is how it would be set up. Now, had you noticed, though, and this is not always something easy to notice, had you noticed the symmetry of the region, what you would have discovered, what you will ultimately discover, is that these two come out to be the same, again, due to symmetry. So you would have gotten the same result had you just integrated one of these and doubled your answer. So either one would have worked. Again, if you think you can pull off that integral, be my guest. Good luck. Let me know if you manage to get that done. Otherwise, you'll just do these two integrals and add the results together. And again, had you been acutely observant, you could have doubled one of them and gotten the same result. So symmetries are always something that is nice to be on the lookout for. All right. Now, this is how it works when you have functions that can be defined in the form f of x or g of x. In other words, x is the independent, y is the dependent. That is not always exactly how it's going to work. It may just depend upon the geometry of the scenario. For example, geometry of the scenario, if you had this curve and that curve, and you're trying to find the area between those two horizontal reference frames, call them C and D, just to prevent confusion. This is not an f of x, this is not a g of x, all right? With the orientation that you see here, what we're gonna have is a x equaling an f of y here, and an x equaling a g of y there. Again, with them being oriented in that way, they are not functions of x, they are functions of y. We will define our area, though, in a very similar fashion. We will define the area in here as being the integral from c to d of f of y minus g of y dy. So with regions that are functions of x, it is upper minus lower. With regions that are functions of y, it is right minus left. And other than that, the procedure is exactly the same.